What's up, team? Grab your coffee. EC2 fundamentals and instance families is dense, but we're taking the scenic route that makes it easy. By the end of this video, you'll be able to look at any workload and pick the right EC2 instance family in seconds, plus understand how auto-scaling and load balancers turn raw virtual machines into a real production system. EC2 is the gateway compute service on Amazon Web Services, and getting the family choice wrong is how teams quietly leak 30 to 50% of their compute budget. Let's fix that. Back in episode 3, we mapped out the global infrastructure, regions hold availability zones, and we treat multi-AZ deployments as the production default because one data center can go dark. But we never opened the door and looked inside. What actually runs in those data centers? That's where EC2 lives, and it's the foundation almost every other compute story builds on. 5 terms anchor everything in this video. Amazon EC2 is the virtual machine service itself. An AMI, short for Amazon Machine Image, is the template you launch from. An instance family is a category of EC2 tuned for a specific workload shape, named by a letter. An auto-scaling group is a managed fleet of those instances, and elastic load balancing is what puts a single front door in front of that fleet. Keep these in your head. We'll touch each of them. A new workload lands on a Code Gorillas architect's desk, an analytics service for a retail client. Before anyone draws a single arrow, one scenario comes first. Should this run on EC2? And if yes, which instance type? That single decision shapes performance and cost for the entire life of the workload. Pick a family that doesn't match the shape of the work, and the client either overpays every month forever, or watches their service crawl during peak load. So let's make sure you can answer it. Here's the one-line definition to anchor everything else. EC2 is infrastructure as a service. Amazon Web Services hands you a virtual machine, and from the guest operating system upward, everything is yours to manage. The patches, the runtime, the application code, the data inside. That single line tells you where the responsibility boundary sits, and it's the line that defines every architectural decision about EC2. Straight from the Amazon Web Services Shared Responsibility Model documentation, EC2 is infrastructure as a service, and that means the customer performs all of the necessary security configuration and management tasks. Notice the word all. There's no middle ground here. When you rent an EC2 instance, you've signed up to patch it, harden it, configure its firewall, and own everything that runs inside it. Think of EC2 as renting an apartment. The building itself, the foundation, the plumbing, the wiring, the lobby cameras, the elevator, that's Amazon Web Services. They maintain all of it. Inside your unit, though, you bring your own furniture, set up your own Wi-Fi, lock your own door, and clean your own carpets. That's the guest operating system, the applications, the data, and the security group rules. Your unit, your responsibility. The landlord doesn't come in and patch your laptop. When you actually launch an instance, you make 5 choices. First, the AMI, the Amazon Machine Image, which is the operating system template and any pre-installed software. Think of it as picking a furnished or unfurnished apartment. Second, the instance type, how much CPU, memory, and network bandwidth the VM gets, and that's the family decision we're about to dig into. Third, the network, which VPC, Virtual Private Cloud, and Subnet, which in turn picks the availability zone. Fourth, storage, the size of the root volume and any extra disks you attach. And fifth, the security group, which is the stateful firewall wrapped around the instance. Instance type names look cryptic until someone explains the format. Take M7G.2 extra large. The first letter, M, is the family, general purpose. The number 7 is the generation, and newer generations are almost always faster and cheaper. The little g after it is an attribute, in this case meaning graviton, which is the Amazon Web Services ARM processor. and 2 extra large is the size, 8 virtual CPUs and 32 gigabytes of memory. Once you can decode the name, the entire EC2 catalog suddenly becomes readable at a glance. Here's the mental model that makes everything else click. You pick the family by the shape of your workload, not by guessing or by what a vendor brochure says. The family letter is a promise about what the underlying hardware is tuned for, the ratio of CPU to memory to disk to network. Match the shape of your work to the shape of the hardware, and everything else falls into place. 5 families. M and T are general purpose, balanced CPU and memory, for web tiers and small databases. C is compute optimized, where the CPU is the bottleneck, video transcoding, high-performance computing, gaming servers. R and X are memory optimized, with lots of RAM per virtual CPU, in-memory caches, large databases, SAP HANA. I and D are storage optimized, with fast local disk, no SQL stores and data warehouses. And P and G are accelerated computing, meaning GPUs, P for machine learning training, G for inference and graphics. Memorize that mapping and you'll answer most family questions instantly. If letters don't stick, think of a rental car lot. The sedan is your M family, reliable for everyday driving. The sports car is C, pure speed, 2 seats, no trunk. The moving van is R or X, built to haul lots of stuff at once, which is your in-memory workload. The dump truck is I or D, moves heavy loads of dirt fast and locally, which is your storage-heavy database. And the Formula 1 car is P or G, wildly specialized for one high-performance job. Renting a dump truck to commute is overpaying. Renting a sedan to move a house is underperforming. Let's drill the mapping with 5 real workloads. A high-traffic web tier is balanced work, that's M family, or T if traffic is bursty. Video transcoding hammers the CPU, so that's C. An in-memory Redis cache needs huge RAM relative to CPU, which is R. A Cassandra cluster wants fast local SSD for random reads, which is I family. And training a machine learning model needs GPUs, which puts you on P. If you can do this 5 workload drill in your head, you've got the family selection muscle that makes these decisions fast and automatic. T family has a twist worth understanding. T instances run at a low baseline CPU, but when they're idle, they earn credits. When a traffic spike hits, they spend those credits to burst above baseline and handle the load. Picture a coffee shop barista with a punch card. Quiet hours, she's filling punches. Rush hour, she's spending them to work faster. Now, here's the part people get wrong. The modern T3, TA, and T4G instances launch in unlimited mode by default, which means they keep bursting past your credit balance for as long as you need, but you pay extra for that surplus burst time. Only the older T2 instances, and any T3 family explicitly configured in standard mode, will fall back to the slow baseline once credits run out. That makes T a poor fit for steady high CPU production load, where you'll either rack up surprise surplus charges or, in standard mode, watch performance drop back to baseline. But it's perfect for dev boxes, low-traffic websites, and anything spiky. Quick checkpoint: you can now read an instance type name, and you can pick a family by matching workload shape to hardware shape. That's huge. But a single EC2 instance isn't a production system. Production needs a fleet that grows and shrinks, and it needs traffic distributed across that fleet. So let's look at the 2 services that turn raw instances into a real system: autoscaling and elastic load balancing. Remember back in episode 2, when we listed the 6 advantages of cloud computing, and one of them was stop guessing capacity? EC2 auto-scaling is the mechanism that delivers on that promise. It automatically adds instances when demand rises and removes them when demand drops, so your running fleet matches actual traffic. No over-provisioning for a peak that might never come. No scrambling at 3 in the morning when it does. An auto-scaling group has 5 moving pieces. First, the launch template, the recipe that says here's the AMI, the instance type, the security group, the IAM role. Every new instance gets built from this. Second, the auto-scaling group itself, the fleet, with a minimum, a maximum, and a desired number of instances spread across your availability zones. Third, CloudWatch, the signal, watching metrics like CPU or request count. Fourth, the scaling policy, the rule that decides how to react, whether that's target tracking, step scaling, scheduled, or predictive. And fifth, the actual add or remove action that adjusts the running fleet. The result is one mechanism doing 3 jobs at once, keeping the service available, matching capacity to demand, and not paying for idle servers. One important note: if you've read older tutorials, you might see something called a launch configuration. Amazon Web Services now recommends launch templates instead, and as of October 1st, 2024, brand new accounts can't create launch configurations at all. They're effectively retired. Launch templates support versioning, work with the newest EC2 features, and are the only modern option. When you see a question or a tutorial mention launch configurations, treat it as legacy. Scaling policies fall into 2 buckets. Reactive policies respond to metrics in real time. Target tracking is the common default. You tell it to keep average CPU at 50%, and it figures out how many instances to run. Step scaling adds different numbers of instances depending on how badly an alarm is breached. Simple scaling is the old one alarm one action pattern with a cooldown. On the right, you have anticipatory policies. Scheduled scaling brings up capacity at a known time, every weekday at 8 a.m. For example, predictive scaling uses machine learning to forecast demand and pre-warm capacity before traffic actually arrives. For most workloads, target tracking alone gets you very far. Now we've got a fleet that grows and shrinks, but clients can't connect to a moving target. They need one stable address. That's the job of elastic load balancing. It gives the outside world one DNS name, and behind that name it spreads incoming traffic across every healthy instance in your fleet. Auto-scaling and elastic load balancing are the inseparable pair that turns EC2 into a real production system. 3 modern load balancers, 3 different jobs. The application load balancer, ALB, operates at layer 7. It speaks HTTP and HTTPS, can route by URL path or by hostname, supports WebSockets, and pairs with Amazon Web Services WAF. The Network Load Balancer, NLB, operates at layer 4. It handles raw TCP, UDP, TLS, and QUIC, which is a modern low-latency transport protocol. It gives you a static IP per availability zone, and sustains extreme throughput with sub-millisecond latency. And the Gateway Load Balancer, GWLB, operates at layer 3. It transparently steers all IP traffic through a fleet of third-party virtual appliances like firewalls or intrusion detection systems. Here it is in one sentence from the Amazon Web Services Elastic Load Balancing documentation. Application Load Balancer is layer 7, HTTP, and HTTPS Network Load Balancer is layer 4, TCP, TLS, UDP, and QUIC. Gateway Load Balancer is layer 3. If you memorize one sentence about load balancers, make it this one. It pins all 3 to their OSI layer and gives you the protocol list you need to pick the right load balancer instantly. Choosing between ALB and NLB is one of the most common scenario decisions you'll face. Reach for ALB when the question mentions HTTP, HTTPS, REST, path or host routing, WebSockets, integration with WAF, or microservices behind one DNS name. Reach for NLB when you see TCP, UDP, TLS, QUIC, a static IP requirement, elastic IP attachment, millions of requests per second, or specific workloads like gaming, Internet of Things, MQTT, or financial APIs that get whitelisted by partner firewalls. The queue is almost always in the protocol list or the static IP requirement. Two more pieces stored inside every running instance. The first is the instance metadata service, reachable at 169.254.169.254. That address belongs on your flashcards. Code running inside the instance can call it to learn the instance ID, the AMI ID, the region, and crucially, the temporary IAM role credentials. Think of it as the card on the hotel room desk that tells you your room number and Wi-Fi password. The second piece is user data, a script you supply at launch time that runs once at first boot to install packages or pull configuration. That's the welcome letter on the pillow, read once and then done. Straight from the EC2 user guide, software running on an instance accesses metadata via the special link local IP address 169.254.169.254. The phrase link local is the key. That address is defined by an internet standard to never leave the local link, which is why the metadata service is reachable only from inside the instance, never from the public internet. Remember back in episode 7 when we covered the Capital One breach? That was an attack that abused this exact endpoint, and it's why Amazon Web Services now defaults new instances to the more secure token-based version 2 of the metadata service. Let's stitch it all into one production flow. Step 1. Pick the family by matching workload shape to a family letter. Step 2. Build a launch template with the AMI, instance type, security group, and a user data script. Step 3. Create the auto-scaling group across multiple availability zones with sensible minimum, maximum, and desired values. Step 4. Attach an elastic load balancer, ALB for an HTTP workload, NLB for raw TCP or UDP. Step 5. Add a scaling policy, usually target tracking on CPU or request count. That 5-step recipe is how almost every classic EC2-backed web service on Amazon Web Services gets built. 5 mental models worth unlearning. Don't pick T-series for steady high CPU work. In unlimited mode, the credits keep flowing, but you pay for every surplus burst second, which inflates your bill. If the group is in standard mode, performance will drop back to the low CPU baseline once credits are exhausted. Don't reach for ALB when the requirement is raw TCP or a static IP. That's an NLB job. Don't reach for NLB when you need path-based routing. NLB doesn't read HTTP. It just forwards packets. Don't follow old tutorials that show you launch configurations. Those are closed to new accounts now. And don't treat user data as ongoing configuration. It runs once at first boot by default. For ongoing changes, you want Systems Manager. 5 things to walk away with. EC2 is infrastructure as a service. Amazon Web Services owns the building. You own the guest OS and everything above. Family letter follows workload shape, M&T balanced, C compute, R&X memory, I&D storage, P&G GPU auto-scaling groups, plus launch templates plus CloudWatch metrics, is the mechanism behind stop guessing capacity. ALB for HTTP and HTTPS, NLB for TCP, UDP, and static IP requirements, GWLB for virtual appliances, and 169.254.169.254 is self-discovery, while user data is a one-time bootstrap. Now let's see how well that landed with a quick 5-question quiz. Alright, time to put your knowledge to the test. Question 1. A media company is building a video transcoding pipeline that runs at near 100% CPU for hours at a time during overnight encoding batches. Memory and disk usage are modest. Which EC2 instance family is the best fit? Is it A, C-series, compute optimized for sustained high CPU, B, T-Series, burstable performance handles long workloads cheaply. C. R-Series, memory optimized for large working sets. Or D. I-Series, storage optimized with fast local SSD. Pause here if you want more time. The right call here is A. Video transcoding is a textbook CPU-bound workload. The codec pegs the processor while memory and disk stay quiet. That's the exact shape the C family is tuned for. T-Series would burn through its credits in minutes. In unlimited mode it keeps going but racks up surprise surplus charges. In standard mode it collapses to the low CPU baseline. Either way, it is the wrong tool for sustained overnight batch work. Question 2. An online gaming platform needs to expose a multiplayer service that uses UDP, must sustain millions of packets per second with the lowest possible latency, and requires a static IP address so partner firewalls can whitelist it. Which load balancer should they choose? A. Application load balancer. B. Network load balancer. C. Gateway load balancer. Or D. Classic load balancer. Lock in your answer before I give it away. This one is B. Network load balancer. 3 keywords in the question all point the same direction. UDP is a layer 4 protocol that ALB simply can't speak. Millions of packets per second with ultra-low latency is NLB's design center, and the static IP requirement seals it. NLB gives you a static IP per availability zone and supports elastic IP attachment. Question 3. An operations engineer needs every new EC2 instance launched into an auto-scaling group to automatically install the company's monitoring agent the first time it boots. Which EC2 feature should they use? A. Instance metadata service at 169.254.169.254. B. An IAM instance profile attached to the ASG. C. A CloudWatch alarm with a scaling policy. Or D. User data script in the launch template. Got your pick? Let's see. It has to be D, and here's why. User data is the purpose-built first bootstrap mechanism, a script you embed in the launch template that runs exactly once when the instance starts. Every new instance the auto-scaling group spins up gets that same script, so installing the monitoring agent happens automatically with zero human involvement. Instance metadata is for reading information about the instance, not for running setup code. Question 4. Let's test a concept from an earlier episode. A security team wants to know who is responsible for installing operating system security patches on an EC2 instance running their company's web application. Under the Amazon Web Services shared responsibility model, who owns this task? A. Amazon Web Services. Patching is part of security of the cloud. B. Shared equally between Amazon Web Services and the customer. C. The customer. Guest OS patching is security in the cloud. Or D. Whichever party owns the AMI the instance was launched from. Think about which side of the boundary the guest OS sits on. The right call here is C. EC2 is infrastructure as a service, which means Amazon Web Services handles the facility, hardware, hypervisor, and host OS, that's security of the cloud. Everything from the guest operating system upward is the customer's job, including patching, applications, and data. That's security in the cloud. We covered this back in episode 7, and it's one of the most important boundaries to understand in practice. Question 5. A retail company runs an e-commerce site behind an auto-scaling group of EC2 instances. They need to route incoming requests so that /API goes to one set of microservice instances, and /images goes to another set, all under the same domain name. Which load balancer should they use? A. Network load balancer. It handles all HTTP traffic. B. Application load balancer. It supports path-based routing. C. Gateway load balancer. It inspects HTTP paths. Or D. Classic load balancer, required for path routing. Run the decision rule from earlier before you answer. The answer is B. Path-based routing, sending one URL pattern to one target group and another pattern somewhere else, is a Layer 7 capability, and only the application load balancer can do it. NLB operates at Layer 4 and doesn't read HTTP at all. GWLB is for transparently inserting third-party network appliances into the traffic path, not for application routing. Whenever you see paths, hosts, or HTTP in a question, ALB is the answer. Closing the book on EC2 fundamentals and instance families. Hit subscribe if you want the rest of the Amazon Web Services, the Amazon Web Services Certified Cloud Practitioner exam mastery delivered without hunting for it. Cheers!